6, 5, 4, 3, 2, 1. Excellent. Beautiful. Very nice.
Hi everyone, my name's Joe Barnard and welcome to the Rocket Factory. This is the room where I build all of my rockets and I thought it would be a more interesting set than my desk. This is Sprint, and what you just saw was the third flight of this vehicle. Here are the main takeaways. Number 1, the pitchover maneuver. That is intentional. It's programmed into the flight software and it worked pretty well. Number 2, the kick at liftoff where the vehicle tilts over. That's not intentional, but it's just an effect of misaligning the thrust vector control mount. It's pretty hard to get right on the ground, but the guidance system handled it pretty well. Number 3, it is so dark, and this one is on me. I usually try to launch at sunset because there's a nice contrast between the pad lighting, the ground lighting, the rocket, the exhaust, and the sky. That's usually a great time to launch because it looks really cool, but if you can't get it right at sunset, you lose a lot of light really quickly. And I played this one too close to the chest. For this flight, the motor failed to ignite twice before finally lifting off on the third attempt. And we have a bit of a theme going here. On the first flight of Sprint, it lifted off right away. On the second flight of Sprint, it took 2 tries. On the third flight, it took 3 tries. It just be like that sometimes. These Apogee F10 motors that I've been using are really hard to ignite, and sometimes it takes a couple of tries. So for the next flight, I will have to launch earlier before sunset so that if something goes wrong, we don't lose all of our light. Number 4, the vehicle was much lighter this time. In an effort to gear up for some of these higher altitude and higher speed flights, I reprinted almost every single part with 1 boundary layer and almost no infill, and I was able to cut back the mass by about 130 grams. Speaking of the mass, let's talk stats for this flight. We got up to 165 meters above ground level on an Apogee F10, and this is an altitude record for thrust vector controlled flights, at least for me. It's definitely not a general altitude record. The runner-up to this flight was the G8ST flight that we did in May of 2018 with an apogee of 132 meters. We were so close to passing it on the last flight, and this one certainly did it. Maximum velocity was 46 meters per second, and you can see it in the plot here. We start off at a normal velocity, something that we would expect from a motor like this, and then halfway through the burn, the vehicle engages like maximum yeet mode or something. Let's look at the acceleration data here. As the burn progresses, things look pretty normal. That thrust curve matches what we see in the data sheet. But as it keeps going, we get this gradual spike in thrust. I am not a propulsion expert. I feel like I say this every video now, but here is what I think is happening. This is what I would refer to as a casing debond. This is a rocket motor. It's a much larger one than a rocket like this would use, but it'll help us explain what's going on. This motor has 2 main parts. We have the casing, which encases the explosion, and then we have the propellant. Here's the nozzle, here's the end cap. This is actually not the propellant. You have small propellant grains that are in here, but high power motors work a little bit differently than the low power ones, so like just go with it. If we assume that this propellant is burning from one end to the other, we would call that an end burner rocket. That's what is used in a rocket like Sprint. Essentially, as this propellant slug is inside of this motor casing, we're burning from the bottom all the way up to the top, and once we reach the top, the motor stops. The amount of thrust we get is a function of a couple of different things, but one of the major things there is how much propellant is burning at once. If you only burn the end, you get a constant surface area of propellant that burns through the whole time. But what if the flame front starts to move up the side and chew off the rocket propellant that's on the side. If it can slip up in between the propellant grain and the casing, if the motor can get inside there, you end up burning much more surface area and your thrust increases. So how can we confirm that this is what's going on with the motor in Sprint? Let's think about it here. If you have more surface area exposed and burning, you're going to burn through all of that propellant faster, right? You're consuming it at a faster rate just because of how things be. So as another reference, let's look at the data sheet for how long the motor is supposed to burn, which is between 6.5 or 7 seconds. And then when we go back into the acceleration data, we can see it's much shorter than that. So we're consuming the propellant at a faster rate. So here's the thing. These are model rockets. This isn't real aerospace. We're not dealing with the tolerances and the quality requirements of the space shuttle boosters. That said, this whole channel is built around pretending I work in the real aerospace industry. So I cut the motor open to see what happened inside. I'll say it one last time, I am not a propulsion expert, so I don't know exactly what to be looking for inside these motors. But I do know how to film things. If you fancy yourself a propulsion expert, take a look at this, see what you think, and let me know in the comments. Finally, we've got the roll program here. I have a reaction wheel up top that tries to roll the rocket 90 degrees about a second after liftoff. That worked great, it looked really stable, and then something happened during the pitch-over maneuver. The vehicle loses control during this maneuver, and initially, here's what I thought. When the vehicle lifts off, it decides what the X and Y coordinates are. Then it does a 90-degree positive roll. When we use the right-hand rule and we put our thumb in the direction of the positive vector, this is a positive 90-degree roll, okay? So we roll positive 90 degrees, the raceway is now on the back. Then when we do our pitch over maneuver, we're pitching over on the x-axis, which is this axis here. So we roll 90 degrees and then we pitch over on the x global axis, which is now the y local axis. I promise this will make sense in a second. When we pitch over this way, we have this free flow airstream that's still coming down because we are not immediately getting all of that horizontal velocity. We're still pitching over into the wind, which is coming this way. And my thought was that this whole raceway here essentially acts like a little bit of a fin. So when we pitch over, we would just lose roll control authority and pitch over like that, or rather roll in this direction. But that's not what happened. When we pitch over, we actually roll in the opposite direction. So I'm not entirely sure what happened here. I'm open to suggestions. In fact, I would like some suggestions. I think we may just be hitting the limit of the quality and the torque capability of the motor I have. I think we may have some weird coupling stuff. Generally speaking, I'm not entirely sure what this is, but I would bet that it could be solved by properly designing a roll control system instead of buying the cheapest components and just sending it. Anyway, if you want access to launch live streams, all of the raw footage, and all of the raw data for this flight and others, that's over on the BPS Patreon linked down below. Thank you so much to the folks who support this project and make it a reality, and thank you to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low.